In the lesson today, we're going to be looking at a very commonly used discrete distribution known as the binomial distribution. And the binomial distribution is going to be very closely related to the Bernoulli distribution, which we've already seen. But what's going to end up happening is going to be slightly more useful. It's going to be a generalization of the Bernoulli distribution. So in today's lesson, really all we want to do is understand what the binomial distribution is, when does it arise, what do we use it for, and then some of the properties for it. So if we think about wanting to do some form of manufacturing, right? And we know that when we're doing manufacturing on a line, some proportion of the products are going to end up defective in one way or another. And if you're the person in charge of running this manufacturing line, you might be interested in knowing, if I produce 1,000 of these products, what proportion of them are likely to be defective, right? If I know that, 1 in 1,000 is defective in 1,000 products, do I expect to have, say, more than 5 defective products? Or what's the probability that I have more than 5? And so the binomial distribution is going to capture this scenario. It's going to capture the scenario where we're doing repeated independent experiments, and each experiment can be a success or a failure. So it's repeated Bernoulli trials. And then from that, we want to know how many successes did we see throughout that whole experiment. Okay. So to put that somewhat more concretely, if you have repeated Bernoulli trials and you count up your total number of successes, the corresponding random variable is going to follow a binomial distribution. Some assumptions we need to make. First is that there's a fixed and a known number of Bernoulli trials that we're going to run, right? So if you remember the geometric distribution, we just continued running trials until we got to a success. In a binomial distribution, we define at the beginning how many trials are we going to run. We also assume that every trial has a constant probability of success. Probability of getting a heads the first time you flip a coin is the same as the 100th, is the same as the 1,000th time. And we also have to assume that each of the trials is independent of all of the other trials, right? And so this is where the binomial distribution sometimes has issues mapping onto the real world, right? So it's worth thinking about in that manufacturing example. Is it equally likely that the first phone and the 100th phone are to be a defective? And is it going to be the case that knowing that the first phone was defective, the 100th phone is no more likely to be defective, right? And that's an assumption that may or may not hold depending on the scenario. Maybe one of the machines is broken down, and so then the whole batch becomes defective, right? Or, but in other situations, it's going to be more viable as an assumption. And when we're able to make that assumption, then the resulting totals are going to become binomially distributed. So we can think of the random variable x as being the counts of successes, and we write that x follows the binomial NP distribution. So there are 2 parameters, and any of the random variables that follow one of these distributions where you vary either of the parameters are going to be from the binomial family distributions. We also have closed form expressions for the expected value and the variance. So the expected value is going to be n times p. And that makes a lot of sense, right? If I tell you that you have a 1 in 10 chance of succeeding at something and you run 10 trials, you would expect that 1 over 10 times 10 is 1 success in those trials. If you expect a 10% chance of success and you run 100 trials, then you'd expect to see 10 successes, right? So that's sort of sensible. The variance is going to be given by n times p times 1 minus p, right? And so we can think about the fact that there's more variance in the total number the closer you are to having probability of 1/2, right? If you're almost certain, right, you push this all the way up to 1 or 0 on p or 1 minus p, then the variance drops to 0, right? If you know every time is going to be a success, there's no variance. You're dealing with constants there. Similarly, if you have always going to have failures, then again, there's no variance. But when you're right around that 1/2 threshold, then you're going to be in a situation where there's sort of as much variance as you could possibly have in that scenario. We can also write down the explicit PMF, and that's going to be given by this expression here, where we have n choose x, p to the power x 1 minus p to the power of n minus x, right? And so back to our counting lecture on what n choose x is going to be, but it's going to take on sort of this closed form expression here. And we could, of course, derive the expected value and the variance using what we talked about in the last lecture from this PMF right here, right? The other thing that I'll point out is that the total number of successes you can have on n trials is going to be anywhere between 0 and n, right? So there's this restricted range as to what x can take on. Now, it's important to remember that the binomial probabilities correspond to sampling with replacement, right? So we have to have that constant probability of success. Every single time that you do something, you have to have an equal chance. If we're thinking about doing something like drawing cards from a deck until we reach an ace, right? Well, the first time that you draw it, you're going to have there's 4 aces in the deck, 52 total cards, and so you're going to have 1 in 13 chance of drawing an ace. But after you've drawn the first card, the probability is no longer going to be 1 in 13, right? Because you're going to only have 51 cards remaining, and maybe you have 4 aces, maybe you have 3 aces remaining. But either way, the probability is going to shift. And so what this would correspond to is if you draw a card, you see whether it's an ace, and then you put it back in the deck, and then you draw another card and you see if it's an ace, right? So it has to be sampling with replacement. If we're sampling without replacement, it's not going to be binomial. If we have a very large population, right? So if you're thinking about drawing from a population of size 1 million, well, then changing the numerator or the denominator by 1 doesn't change very much, and so it will behave approximately as a binomial. But remember that in a finite population, we're not going to be following a binomial distribution, and we'll talk a little bit more about this later on. So that's the summary for the binomial distribution. It's going to be a distribution that characterizes us counting the number of successes in repeated Bernoulli trials. We have a closed form for the PMF, which is given by n choose x, p to the power of x, 1 minus p to the n minus x. We have a closed form expected value, a closed form variance. And we're relying on these 3 core assumptions. So there's going to be a fixed number of trials, a constant probability of success, and independence between the different trials, right? And so if you have that, then you wind up with a binomial distribution, and this is going to come up all over the place. So it's a distribution that you'll become very familiar with. In the next lecture, we'll be taking a look at other discrete distributions, and so I hope to see you all there.